Beneath the ground we walk on exists an entirely separate world of life, one that operates without sunlight, moves in geological time, and challenges everything we thought we knew about the boundaries of life itself. Join us as we explore the vast, mysterious ecosystem of Earth's deep subsurface, where microorganisms survive in conditions once thought impossible and may represent the dominant form of life not just on our planet, but potentially throughout the universe. In 2018, after a decade of intensive research, the Deep Carbon Observatory made a discovery that would shake the foundations of biological science. They revealed that living organisms exist up to 5 kilometers below Earth's surface and seafloor, constituting between 15 to 23 billion tons of carbon biomass. That's nearly twice the amount found in all humans on Earth. But what makes this discovery truly revolutionary is that this massive ecosystem operates almost entirely disconnected from the surface world's photosynthesis-based energy systems. As Dr. Tullis Onstead of Princeton University, a pioneer in this research, explains, we've discovered an entirely separate biosphere. These organisms don't care if the sun exists. For centuries, our understanding of biology centered on the premise that all life ultimately depends on solar energy captured through photosynthesis. The discovery of the deep biosphere completely inverts this paradigm, showing us that vast ecosystems can thrive using chemical energy derived from rock-water interactions, utterly independent of sunlight. The scale of this subsurface ecosystem is staggering. Recent surveys by the International Ocean Discovery Program suggest that this subterranean world may extend as deep as 10 kilometers in certain regions, with microbial communities somehow adapting to pressures exceeding 1,000 atmospheres, pressures that would crush most surface organisms instantly. Dr. Verena Hoyer at the University of Bremen has documented over 6,000 previously unknown microbial species in just 3 years of research, suggesting we've barely scratched the surface of subsurface biodiversity. These organisms haven't simply survived in these extreme conditions. They've evolved specialized metabolic pathways that allow them to extract energy from minerals and gases that would be toxic to surface life. This represents parallel evolutionary trajectories that have been hidden from our view for billions of years. These microbes aren't just surviving deep underground. They're thriving in ways completely different from surface life, using chemical pathways we never knew existed until recently. Perhaps most astonishing is the metabolic pace of these deep microbes. Research led by Dr. Karen Lloyd at the University of Tennessee has revealed that some subsurface microorganisms have life cycles operating on timescales previously thought impossible for living entities. We found microbes that may divide once every 10,000 years, Lloyd notes. Their metabolic rates are so slow that they're effectively living in geological rather than biological time. This extreme slow-motion existence challenges our fundamental assumptions about the minimum energy requirements for life itself. Some deep microbes survive on less than a zeptajoule. That's 10 to the power of minus 21 joules of power per second, approximately 100 millionth the energy needs of surface microbes. The implications are profound. These organisms essentially exist in a state resembling suspended animation, blurring traditional definitions of dormancy. A 2020 study published in Science Advances demonstrated that certain subsurface archaea can repair DNA damage and maintain cellular integrity while consuming almost immeasurably small amounts of energy. This suggests biological processes can occur at rates previously considered thermodynamically impossible. Dr. James Bradley at Queen Mary University of London has proposed that these ultra-low energy states may represent the dominant mode of life in the universe, not the energy-intensive metabolisms we observe on Earth's surface. His mathematical models indicate that up to 60% of Earth's prokaryotic life may exist in these near-zero energy states, with generation times measured in centuries rather than minutes or hours. This fundamentally changes our understanding of what life means in the cosmic context. If most life on Earth, and potentially throughout the universe, exists in these ultra-slow, ultra-efficient states, then our surface-based understanding of biology represents only a tiny fraction of how life actually operates. The implications for astrobiology are enormous. If life can persist with such minimal energy requirements, the potential habitable zones on other planets and moons expands dramatically. Research published in 2021 by the Japan Agency for Marine Earth Science and Technology team revealed that these subsurface communities transform inorganic carbon compounds through novel metabolic pathways previously unknown to science. Dr. Fumio Inagaki's team discovered microbes that can convert methane and carbon dioxide into more complex carbon compounds without photosynthesis, effectively creating a parallel carbon cycle independent of surface processes. This finding suggests that significant portions of Earth's carbon budget may be regulated by processes we've been unaware of until recently. We need to fundamentally revise our understanding of global carbon cycles, Inagaki argues. Between 15 to 30% of Earth's carbon transformations may occur in the deep biosphere, completely invisible to surface-based observations. The implications for climate science are substantial. Current carbon cycle models, which inform climate change predictions, largely ignore subsurface biological processes. A 2022 paper in Nature Geoscience demonstrated that deep microbes in continental crust consume approximately 0.5 gigatons of carbon annually, a significant flux that remains unaccounted for in most climate models. This underground carbon sequestration may act as an unrecognized buffer in Earth's climate system, potentially explaining certain discrepancies in atmospheric carbon budgets that have puzzled scientists. Perhaps most revolutionary is the growing evidence that these microorganisms actively participate in mineral formation and transformation, effectively serving as geological agents. Research from the Center for Dark Energy Biosphere Investigations has demonstrated that certain deep microbes can accelerate the weathering of basalt by up to 126 times, releasing nutrients and creating microhabitats. Others precipitate minerals directly, forming structures that persist for millions of years. We're finding microbial fingerprints in rocks we previously considered abiotic in origin, explains Dr. Bénédicte Ménez of Institut de Physique du Globe de Paris. These organisms don't just inhabit the subsurface, they engineer it. A 2022 study in Nature Geoscience revealed evidence that microbial communities may have played critical roles in forming certain copper and gold deposits by creating the chemical conditions necessary for metal concentration, suggesting that some valuable mineral resources may be partially biogenic in origin. This biogeological interplay extends beyond metal deposits. Dr. Maggie Lau from the Chinese Academy of Sciences has documented how subsurface microbes transform clay minerals, altering their water retention properties and effectively changing the hydraulic conductivity of deep aquifers. This microbial geoengineering may influence groundwater movement patterns across continental scales, affecting water availability in ways we've never considered before. These discoveries have profound implications for astrobiology. The European Space Agency has begun incorporating findings from deep subsurface research into the design specifications for future Mars and Europa missions, recognizing that if life can thrive in Earth's subsurface without photosynthesis, similar environments elsewhere become much more promising targets. Mars, for instance, has lost most of its surface water and has minimal atmosphere, making surface life unlikely. But its subsurface may maintain conditions similar to Earth's deep biosphere. Similarly, Europa's ice-covered ocean might host life not at the ice-water interface as previously thought, but deep in the Moon's rocky core where water-rock interactions could provide chemical energy similar to what powers Earth's deep biosphere. The discovery that life can exist with minimal energy, in high-pressure environments, and without any connection to photosynthesis dramatically expands where we might find life in our solar system and beyond. If the dominant mode of life in the universe is indeed these slow metabolism, rock-dwelling microorganisms, then we've been looking for life in all the wrong places, focusing on surface environments that might actually be the exception rather than the rule for biological habitats. Beyond pure science, these organisms offer unprecedented biotechnological potential. Researchers at the Bigelow Laboratory for Ocean Sciences have isolated enzymes from deep subsurface microbes that remain active under conditions that would denature conventional proteins. One enzyme, extracted from microbes living in 121 degrees Celsius hydrothermal systems, has shown promise for breaking down microplastics under extreme conditions, potentially offering new approaches to environmental remediation. The extremophile enzymes found in the deep biosphere could revolutionize industrial processes by allowing reactions to occur at higher temperatures, pressures, and in the presence of solvents that would destroy conventional biological catalysts. These microorganisms have evolved solutions to problems we're still struggling to solve, from energy efficiency to material transformation. Their unique metabolic pathways might inspire new approaches to carbon capture, mineral extraction, and waste remediation. Some researchers are already exploring how these organisms might be harnessed to help address environmental challenges, from cleaning up contaminated groundwater to developing more efficient industrial catalysts that work under extreme conditions. Perhaps most profoundly, the deep biosphere challenges our philosophical conception of life. These organisms, operating on timescales of thousands of years, with energy budgets barely above theoretical minimums, transforming rock into biology and back again, blur the boundaries between living and non-living systems. We need to reconsider what we mean by alive, suggests Dr. Lloyd. When an organism's life cycle operates on geological rather than biological timescales, it forces us to question whether our definitions of life have been too narrow, too focused on surface world paradigms. These microorganisms exist in a state that challenges our binary distinction between living and non-living. They operate at energy levels so low they approach the theoretical limits of what's required for life, yet they maintain genetic integrity, respond to their environment, and reproduce, albeit on timescales we can barely comprehend. If an organism divides once every 10,000 years, is it experiencing life as we understand it? Or is it something else entirely, a biological-geological hybrid that exists in a category we don't yet have language to describe? As we continue exploring this vast subsurface ecosystem, which may contain up to 70% of Earth's bacterial and archaeal life, we need to fundamentally revise our understanding of Earth's biogeochemical processes and our very conception of what constitutes a living planet. The discovery of this shadow biosphere beneath our feet reminds us that even on our own world, life's ingenuity and adaptability exceed our imagination. For centuries, we've studied Earth's surface in exquisite detail, cataloging millions of species and mapping ecosystems across the globe. Yet all this time, a vast, alien ecosystem has existed right beneath us, one potentially larger than all surface life combined. This revelation comes at a critical moment in human history, as we face unprecedented environmental challenges in search for life beyond Earth. The deep biosphere offers both practical insights into how life can persist in extreme conditions and philosophical perspective on our place in the cosmos. If most of Earth's life exists in forms and places we've only just discovered, how much more remains unknown? And if life can thrive in such unexpected environments on Earth, how might it manifest on other worlds? The deep biosphere represents not just a new frontier for science, but a humbling reminder that life's potential extends far beyond the narrow parameters we once defined. As we continue to explore this hidden realm, we may find that throughout the universe, life exists in forms and places far stranger than we dared to dream. The discovery of Earth's deep biosphere represents one of the most profound scientific revelations of our time, a hidden world that fundamentally changes our understanding of life itself. Operating in near isolation from the surface, these extraordinary microorganisms survive with energy budgets approaching theoretical minimums, reproduce on timescales measured in millennia, and actively shape the geology of our planet. They've created parallel carbon cycles, influenced mineral formation, and blurred the very boundaries between living and non-living systems. Beyond expanding our understanding of Earth's processes, this shadow biosphere transforms how we search for life elsewhere in the cosmos and offers unprecedented biotechnological opportunities. As we continue exploring this vast ecosystem, potentially containing the majority of Earth's microbial life, we must reconsider what it means for a planet to be living. The deep biosphere reminds us that life's adaptability exceeds our imagination, suggesting that throughout the universe, biology may thrive in environments and forms we're only beginning to comprehend. In the slow, patient metabolism of these ancient organisms, we glimpse both Earth's history and the possible future of life across the cosmos. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.